and we'll talk about the warm-up problem. Okay, 66% of you got it correct, and 66% of you said it was curve 3, the blue curve. Okay, so let's figure out what's going on here. You're trying to find the protonated form of the weaker acid. So let's talk about these curves. So when I think about these curves, what I always think about first is I think about the equilibrium. So we're thinking about a weak acid. So the weak acid is going to be in equilibrium with its dissociated form like this. Now, Le Chatelier says if you add protons, you are going to shift to the left. So you're going to shift like that when you add protons, or in other words, you are going to shift to the left as you add acid. In other words, when there are lots of protons around a very acidic solution, you will go to the protonated form. Okay, so that's the first piece of reasoning that you need. The second piece of reasoning is you need to understand what these curves are trying to say. Okay, so remember that these curves are trying to tell you about the relative concentrations of the protonated and deprotonated forms of either a weak acid or a weak base, in this case, a weak acid. Now, since this is being plotted as a function of pH, you go more acidic, you go to HA. That means the left-hand curve is going to represent HA, the protonated form. The right-hand curve represents A minus. And then the place where these two cross, the 50-50 point, is going to be the pKa. Okay, so the second thing you needed to realize was that if you have a weaker acid, of course, what that means is that you are going to have a smaller Ka. And if you have a smaller Ka, that means that you have a larger pKa. So you should have chosen the one to the right and chosen the protonated form. Okay, so that's how you do that one. Quick announcement, group quiz 7 was posted last night. So it is going to be due next Thursday, 4/15 at 5 p.m. And of course, group quiz 6 is going to be due tomorrow also at 5 p.m. Okay, so at the end of the last lecture, we started talking about this mildly scary diagram. So let's go through this again. What we're trying to do is figure out what is the pH of a solution after you mix an acid or a base. And to understand that, you have to understand where you are in this process. So what we said was, let's suppose that we start out by looking at our acid and figuring out how many moles of protons we could get from it if we completely dissociated it. And let's say we could get A moles of protons out of our acid, and we did the same thing for the base. We asked how many moles of OH minus could we get from our base if it was completely dissociated. So that gives us how much acid and how much base we have. Now, if we have equal amounts of acid and base, that's the point of neutralization. Okay, so at that point, we are neutralizing the acid with a base. When we're doing a titration, this is called an equivalence point. And what you are doing is you are completely making a salt. So in this case, where A is equal to B, the pH is simply going to be a pH of the salt solution. And you are going to know that you are going to have A, which is equal to B, which is equal to that many number of moles of salt. Okay, so that tells you where you are when you have A is equal to B. Now, what if you have A and it's bigger than B? So you have more acid than base. Well, if you have more acid than base, you are going to be up here, and you are going to have all of your base is going to react with your acid. And when all of your base reacts with your acid, it makes salt, and it makes B moles of salt. But there's going to be acid left over. How much acid? Well, there's going to be A minus B acid left over. And so now what you do is you figure out how to calculate the pH. If your excess acid is a strong acid, what we're going to do is we're going to neglect the salt because the pH of the excess acid is going to dominate the calculation. And so you just calculate the pH of the excess acid, and you are going to have A minus B moles of your excess acid. On the other hand, if you have a weak acid, then you have made a buffer, and we'll talk a little bit later on about how to calculate the pH of a buffer. Now, you could also be in the case where you have more base than acid. In that case, A would be less than B, and if A is less than B, all of the acid will react with base to give you salt. So you will have A moles of salt, and then you'll have excess base, and you will have B minus A moles of base left over. Then you do the same kind of decision. If we have a strong base, then we're going to be able to ignore the salt, and we're just going to calculate the pH of the excess base, and we are going to have B minus A moles of our excess base. On the other hand, if we're dealing with a weak base, we have made a buffer, and so we'll talk about how to calculate the pH of a buffer. Okay, so this is how you're going to attack these problems, and it all starts from right here, figuring out how many moles of protons you have, moles of OH minus, and then figuring out where you are in this manifold. Okay, and it will become clearer as we work through this. But let's see if you can do one of these. So let's start with a simple problem. Okay. So I'd like you to calculate, if you have a 5 ml sample of 2 molar formic acid, how many mils of half molar calcium hydroxide will be needed to reach the equivalence point?
Usually very introspective people. These just sends you on a mental thought trip.
I'm already almost always on mental thought trips, but most of which kind of suck. So why would I want to make that a more intense experience?
Because take it. Some form of introspective experience.
The problem is that most people when I take it, I just end up getting really anxious. And then
Many of you are making a silly answer. Double check.
I had that really badly last time.
That just happens to me almost every time.
I never had it before. I never had it before. And there's multiple times. And last one, so I just had too much paranoia and shit. I'm gonna have a quick break, guys. Didn't touch it really.
Okay, let's get those final answers in. Okay, a third of you got it correct. And a third of you said it was 10 mils. But if you will notice, if I can find the one, there, where is it? There are a bunch of you that said 20 mils. Yes, there, look at that, 20 mils. 30% of you said it was 20 mils. Now, why did 30 of you make that mistake? Well, let's try and see what's going on here. Well, the first thing you're going to say is that when you are at equivalence, well, at equivalence, you're going to have equal amounts of acid and base. So what you say is that the equivalent number of moles of protons are equal to the equivalent number of moles of OH minus. And then you just calculate these two things. So the moles of protons, you're going to have a 5 mil sample of your formic acid. So you say 5 milliliters of formic acid, and it's 2.0 moles per liter. So it's going to be a 2.0 molar solution. And then you are going to get 1 proton for every HCOOH. Okay, and now the moles of hydroxide, you don't know how much volume you have, so you are now going to multiply this by the concentration, which is 0.50 molar calcium hydroxide, so you're going to have moles per liter. And then, where many of you got screwed up, you need to say that you are going to get 2 OH minuses from every calcium hydroxide. And if you forget this factor of 2, your answer will always be off by a factor of 2. Okay, so I can cancel out my moles per liter, and then what I can do is I can have 2 times 0.5 gives me 1, And so what I'm going to have in the end is that V is going to be equal to 5.0 milliliters times 2.0, which is going to be equal to 10 milliliters. Okay, so that's how you figure out where the equivalence point is. And really, it's a very straightforward calculation once you realize that you start with moles of protons is equal to moles of OH minus. Okay, so that's how you find out where the equivalence point is. Let's now go a little bit deeper in this, and let's start talking about titration. And I'm going to start with the titration of a strong acid with a weak base. Strong acid with a strong base. And this is going to be essentially the same thing as the titration of a strong base with a strong acid. Okay, so the key thing here is that you are going to make an assumption. And what you are going to assume is that since a strong acid plus a strong base gives you a neutral salt, you are going to assume that your pH at your equivalence point is going to be equal to 7.0. And that's going to be because you are making a neutral salt. Okay, so let's work this by an example. So for example, let's suppose I ask you to calculate the pH when 20 mils, so when 20.0 mils of 0.500 molar HCl is titrated with 1.00 molar sodium hydroxide. Okay, so first let's draw a picture of this because there is a common place where people are going to make an error. So you have a beaker. Into this beaker you have your HCl. And then what you do in the titration is you are going to be adding your NaOH. And so the important thing to realize here is that the volume is going to be changing continuously. And that's going to be important when you calculate all of your concentrations. You have to keep track of the fact that your volume is changing. Okay, so how are we going to do this? We're going to do this in a couple of steps. The first step is going to be to calculate your initial moles of protons. And so these are going to be the moles of protons in the HCl, or if you were doing a strong base, strong acid, you would calculate the number of moles of OH minus. So whatever is in the beaker initially. And so to do that, we say that our moles of OH plus, our moles of H plus is simply going to be equal to, well, we're going to have 20 milliliters, so 20.0 milliliters of 0.500 moles per liter of HCl, and I'm going to get 1 proton for every HCl. Okay, so now what I can do is I can cancel out my liters, and then I can multiply this out, and this is going to give me 10.0 millimoles of H plus. Okay. Now, this is what you're going to be neutralizing during your titration, so that's why we want to know that. And now the second thing is we're going to figure out where our endpoint is. So what we're going to do is we are going to calculate the volume of OH minus, which in this case is coming from the sodium hydroxide, or the H plus if we were dealing with this in reverse, to reach the equivalence point. Okay, so that's pretty straightforward. We know that when we're at equivalence point, the moles of protons must be equal to the moles of OH minus. Now, I just calculated the moles of H plus, so I know that I'm going to have 10.0 millimoles of H plus at equivalence. And then I want to know how much volume, so volume is going to be V, and then I'm going to multiply this by my concentration, which is 1.00 moles per liter, and then I am going to get 1 OH minus for every sodium hydroxide. Okay, so that's going to be that, and now what I can do is I can cancel out my moles on both sides, And what I'm going to be able to do is I'm going to be able to solve for V. And so I'm going to find that V is simply going to be equal to 10.0 milliliters. Okay, so that gives me my volume at equivalence. And now what I have to realize is that there are going to be three regimes. Let me just write this volume down here so I can get a little bit of space. So it's going to be 10 milliliters. Okay, now what I want you to realize is during this titration, there are going to be three regimes that you are going to have to worry about. So there are going to be three regimes of our titration. Okay, and what are the three regimes? Well, the first regime is going to occur if the volume that we have added is less than 10.0 milliliters. The second regime is when we have added exactly 10.0 milliliters. And then the third regime is going to be when we are past 10.0 milliliters. Okay, so if the volume is equal to 10 milliliters, well, that's when we are at the equivalence point. And so what we are going to have there is we are just going to have a salt. And we are going to know that this is going to be a neutral salt, so we're going to know immediately that our pH is going to be equal to 7.0. However, if we are less than the equivalence point, that means we still have acid left, so we are going to have excess acid, but we have possibly added some base to make some salt. So in this regime, we're going to have excess base plus our salt. But we're going to make the assumption that the acid is going to dominate because it's a strong acid. And so what we're going to do is we are going to neglect our salt in the calculation, in our pH calculation. Similarly, if we're in the regime where we are past the neutralization point, we are going to have excess base because all of our acid has now been neutralized to make salt. But again, we are going to neglect the salt because we have a strong base which is going to dominate the pH. Okay, so really we're doing either an excess acid or an excess base calculation unless we just happen to be at neutralization, and then we just write down the answer for what the pH is going to be. Okay, so that's how that happens. Let's now take a closer look at what's going to occur in this titration. And so what I want to do is I want to walk slowly through the titration, looking at how the pH changes, because I know that all of you understand what a titration is, but maybe not in the detail that we would like you to. So what I'm going to do is I'm going to walk through the titration, and I'm going to keep track of how much sodium hydroxide I have added at any point. And the units on this are going to be milliliter. So that's going to be the first column in my table. And then from that, I'm going to calculate how many millimoles of OH minus I have added. Okay, so I'm just going to calculate that from how much sodium hydroxide I have added. And then the next thing I'm going to do is I'm going to keep track of the millimoles of my excess reagent. And my excess reagent is going to change, remember. Early on, my excess reagent is acid. Past the neutralization point, the excess reagent is going to be base. Okay, the next thing I'm going to keep track of is I absolutely have to keep track of my total volume because that's going to influence my concentrations, and the total volume changes continuously in a titration. Then the last thing I need to do is I need to calculate the concentration of either my H plus or my OH minus, whichever is going to be in excess, and I'm going to use that then to calculate my pH. Okay, so this is going to be our titration, so let's just walk our way through it. So let's start out when we have not added anything at all. So we haven't added any sodium hydroxide yet. So because of that, there are no millimoles of OH minus that we have added yet. And we know then that there are going to be 10 millimoles of excess H+, because I just calculated that. So we have 10.0 millimoles of H+ that's going to be in excess, and our total volume that we're starting with is going to be 20 milliliters, and so I can calculate a concentration that's going to be 0.50 molar. Plug that into my calculator. That tells me the pH is it's 0.30. Okay, so it starts out very acidic. Now what I'm going to do is I'm going to go halfway to neutralization. So halfway to neutralization is going to be adding 5 milliliters of sodium hydroxide. So at this point, I am going to have added 5 millimoles of OH minus. That reacts with the H plus, leaving behind 5 millimoles of H plus. So H plus is still my excess reagent, and now I have a total volume of 25. When I plug this into my calculator, my concentration comes out at 0.20 molar H plus, which gives me a pH that is going to be 0.70. So notice I am halfway through my titration. My pH has barely changed. Okay, let's go 90% of the way. So if I go 90% of the way, I have now added 9 molars. So I am now 90% complete. So I've added 9 milliliters, which means I have added 9 millimoles of OH minus, which means I have only 1 millimole of H plus. Now my total volume is 29. My concentration now is going to be 0.034. 90% complete, you might think, oh, now I'm really going to have a change in pH. Actually, not so much. You're going to be at 1.47. Now, does that make sense? Well, actually, it does make sense, because notice the amount of excess reagent has gone down by a factor of 10. So without worrying about the change in volume, that means you should expect that your pH is going to change by about 1 unit. And indeed, that's what happened. It went from 0.3 to 1.47. Okay, that's 90%. Let's go 99% of the way there. So let's add 9.9 milliliters. So we add 9.9 milliliters. Now we are 99% complete. Okay, so we have almost finished this. I should say that this 90% complete, at this point, you are at a pH of straight lemon juice, pretty much. 99% complete, so we're almost finished. Now we've added 9.9 millimoles of OH minus. We have 0.1 millimoles of H plus in excess. Our volume is 29.9. Plug this into our calculator. Our concentration is 0.0033. Okay, what's happened? Notice that the amount of H plus has gone down by another order of magnitude. So that should only change the pH by 1 unit. And indeed it does. We are up to 2.48, even though we're almost finished with our titration. And at this point, the pH is the same as Coke. Okay, the drink. Okay, so let's go to where 99.9% complete. And so now we have added 9.99 millimoles, and we are going to have 0.01 millimoles of H plus in excess. And we are at 29.99 milliliters. And our new concentration is going to be 0.00033. So again, you should expect another unit of pH. And even though we're almost through, indeed, our new pH is going to be 3.48. So here we are 99.9% complete. And so at this point, we're going to have a pH of seltzer. So it's still quite acidic. Okay, let's just go on and take it to completion. So at completion, we've added 10 mils of sodium hydroxide. We've added 10 millimoles of OH minus. We no longer have an excess reagent. Our new total volume is going to be 30. And our new concentration, it doesn't matter because now we just have water, and our pH is going to be 7. Okay, so this is the neutralization point. Let's go just a tid past. So let's just go to 10.01, okay? So this is the equivalent of the 9.99, but on the other side. So now we have 10.01 millimoles of OH minus added. So we have 0.01 moles of OH minus, millimoles of OH minus in excess. So see here, we flip from being H plus in excess to OH minus in excess. Our new total volume is 30.01. And let's just cut to the chase. The pH now is going to be 10.57. Okay, so this is now going to be at 100.1% complete, and your pH is going to be that essentially of Clorox. So what I want you to notice here is what happens right between these three measurements, okay? So this is 2/100ths of a milliliter. So this is going to be on the order of a quarter of a drop. Okay, so there is no way you can do a titration this accurately. And notice what has happened here. Our pH went from 3.5 to 10.5. So that's a 7 pH unit change over the course of a quarter of a drop. So don't think that you can do a strong acid, strong base titration and hit a pH of 7, because you can't. You can't do anything nearly that accurately. You're always going to overshoot, and you will typically overshoot dramatically. You need to think about this when you're mixing acids and bases in the indicator lab. Okay, so let's go a little bit further. Let's go until we're a milliliter past. So we've added 11 mils of sodium hydroxide, or 11 millimolar of sodium hydroxide. Now we are going to be 1 millimolar in excess, and so we are going to be 1.0 of OH minus. And when we calculate out our total pH, our pH is now 12.5. And if we go up until the point where we add an infinite amount of sodium hydroxide, then our pH is just going to be the pH of our starting titrant. And so our pH is going to be equal to 14. And so this is going to be the pH of the titrant. So the important thing I want you to see here is that initially in your titration, basically nothing happens. Your pH pretty much stays the same until you're almost finished. And when you're almost finished, your pH just rockets, and it rockets past 7 until you start getting near a pH of your titrant. So let's try to bring that home by drawing a picture of what is going on. Okay, so let's draw a picture of this titration. So what I'm going to do is I am going to plot pH on my vertical axis. And I'm going to put the volume of the titrant, the stuff I am adding, on the x-axis. So this is going to be the volume of my titrant as a function of pH. And let's make the pH go from 0 up to 14. Okay, so what I want to do now is I want to draw some guidelines. And the important guideline for the vertical axis is going to be at 7. And then for the x-axis, we will start at 0, and the important point is going to be the neutralization point. And so the neutralization point, remember, we calculated was going to be at 10 milliliters for this problem. Okay, so at neutralization, we know that we are at a pH of 7. The other thing that we showed was we started out at a very low pH of about 0.3, and as we add base, yes, the pH does increase, but it does so very, very slowly. until you're almost finished. And it's only when you're like 99% finished that it's going to rocket up, and then it goes essentially straight up, hits the 7, and keeps going and before it then rolls off, and then does the same kind of thing, where it is almost constant. Okay, so this is what a strong titration is going to look like. There are going to be some important points. One important point is going to be our equivalence point. Our equivalence point is going to be at a pH of 7 because we're making a neutral salt. The first part of this titration curve is going to be almost flat. The pH essentially does not change before you get to the equivalence point. Same thing afterwards. You're going to be almost flat. And then around the equivalence point, things get very exciting. This is going to be where this line is going to be almost vertical. So your pH changes dramatically over a very small amount of added base. Okay, in the point to the left of the equivalence point, what you're going to have is excess acid plus some salt, and we're going to ignore the salt. On the right-hand side, you are going to have excess base plus some salt, and we're going to ignore the salt. Okay, so the important thing that you want to remember of this is that you cannot hit your equivalence point in the lab under typical conditions. So you can't hit your equivalent point in a strong titration. And the reason is because this part of the curve changes so dramatically over a very small amount of added, in this case, base. So remember this when you go into the lab this week and next week. This is very important. Okay, so that's how what a strong titration looks like. Let's try a quick learning catalytics to see if you understand that. Okay. So the graph below describes the titration of which analyte by which titrant. Okay, let's get those final answers in. Okay. So 50% of you got it correct and said it was barium hydroxide being titrated by HCl. So let's see how you could have figured that one out. Okay, so the first thing is you notice that the pH starts very basic. And so you had to start with a base. The only base that was in the list was going to be barium hydroxide. And so you immediately know that your analyte is equal to a base. Therefore, it had to be barium hydroxide. Now, the second clue here is the equivalence point. And it was pointed out to you that the equivalence point was equal to 7. And so that's another clue. And so if the equivalence point is going to be at a pH of 7, that implies almost always that what you're going to have is a strong plus strong titration. The only other way you could get a pH of 7 was if the Ka of your acid was exactly equal to the Ka of your base. But the base is a strong base, so that doesn't matter. So the Ka is equal to the Kb. So this is going to be a strong, strong titration. That means it had to be HCl, the only strong acid that was available. Okay, so that's how you look at these titration curves, and you're going to get many more opportunities to do this, including in the lab. So let's move on now, and let's start our discussion of buffers. Because I've mentioned buffers, but I haven't really said what they are. Okay, so let's just talk about what they are. So you can make a buffer in one of two ways. You can have a solution of a weak acid plus the salt of its conjugate base. And this is the first way you could make a buffer. And there are two things that are important here. First, it absolutely has to be a weak acid. It doesn't work if it's strong. And the second thing, it has to be its conjugate base, not just some random conjugate base you found in the cupboard. Okay, so that's one way you can do it. Or you could make it by taking a solution of a weak base, and you take the salt of its conjugate acid. And so this is the second way we're going to be able to make a buffer. And again, this absolutely must be a weak base and the salt of its conjugate acid. Okay. Okay, so that's going to be how we are going to make a base, make a buffer. So let's look at some examples of buffers. So let's look at some examples of number 1. Okay, so the first type of buffer, what we're really doing is we are dealing with a usual weak acid, weak base, a weak acid equilibrium. So we have HA being in equilibrium with H plus A minus. And so we are going to be using an acid, in this case it's going to be a weak acid, and we are going to be using its conjugate base, which here is going to be A minus. So, for example, if you wanted to use A as your weak acid, you could have HA, and you could mix that with sodium A, okay? So that's one possibility. Or you could take, for example, HF, and you could mix that with potassium fluoride, KF. Or you could take HCN, and you could mix that with calcium cyanide, like that. So in all of these cases, it's going to be a weak acid and the salt of its conjugate base. Okay, that's fine. Let's look at number 2. Well, if we're looking at number 2, we're dealing with a weak base equilibrium. So the equilibrium we are interested in is base plus water is going to be in equilibrium with base H plus OH minus. Okay, so now we are going to have a weak base, and we are going to have its conjugate acid. Okay, so let's give a few examples. If we wanted to just use an arbitrary B, for example, we could take B and add it to B hydrochloride. That would make a buffer. Another possibility would be to take ammonia, NH3, and mix that with NH4Br, ammonium bromide, like that. Okay, so these are some some buffers made from acids and buffers made from bases, but there are also many, many things that are not buffers, and you have to be able to recognize that as well. So for example, if I took HF and I mixed this with ammonium chloride, this is not going to be a buffer, okay? This is a weak acid plus the salt of a weak base, and I don't even know what this thing is, so that is definitely not going to be a buffer. Similarly, you are not going to be able to take HCl and mix it with sodium chloride. And the reason is because HCl is not a weak acid, so this is not going to give you a buffer. So you have to follow the rules to get a buffer. Okay, so that's what a buffer is defined as. Let's try and figure out what the pH of a buffer is. And then next time we'll talk about why we care about these and what is so special about buffers. Okay, so let's do this by example. So for example, let's ask what is the pH of a general solution that starts out having some initial concentration of acetic acid, which I'm going to call HAC, and our initial concentration is HAC naught. So HAC is going to be acetic acid, which is otherwise known as just vinegar. Okay, and we are going to mix that with some initial concentration of sodium acetate. Okay, so that's going to be our initial sodium acetate. And then what we are going to do is we are going to assume, and this is a great assumption, complete dissociation. Okay, and so if it completely dissociates, what we're going to be able to do is take our initial concentration of sodium acetate and just replace it with the concentration of acetate. Okay. Now all we have to do is look at our weak acid equilibrium. So we're going to start with acetic acid is going to be in equilibrium with a proton plus the acetate ion. The pKa of this equilibrium is going to be equal to 4.74. Or if you prefer to think about Kas, this Ka is going to be equal to 1.8 times 10 to the minus 5 molar. Okay, now everything from this point on is just an ice table, and it's straightforward. So now we have our initial concentration. Our initial concentration of acetic acid was the concentration of acetic acid naught, no protons, and then we had our initial concentration of acetate ion. Now our change, the only thing that can happen is some of the acetic acid can dissociate because we have no protons. So we'll have minus X acetic acid plus X protons plus X acetate. Then we will come to equilibrium. Our equilibrium concentration will be the initial concentration of acetic acid minus X. Then we'll have X, then the initial concentration of acetate plus X. Now, can we make an approximation? That's a pretty small equilibrium constant, so I would say yes. So we're going to make an approximation, and our approximation is going to be that X is much, much less than either one of these. So I'll say it's much, much less than the initial concentration of acetic acid and much, much less than the concentration of our acetate ion. And in that case, we're going to be able to say this is going to be approximately the concentration of acetic acid, then we'll have X, then we'll have the concentration of acetate minus, like that. Okay, now we plug this into our equilibrium expression, and our equilibrium expression is going to be the concentration of H plus times the concentration of AC minus divided by the concentration of HAC is going to be equal to K sub A. Now we read off from this line. So for the concentration of X plus, we're going to have H. Then we're going to have the concentration of acetate naught up top. And then we're going to divide by the concentration of acetic acid naught. Okay, so now what we're going to do is we are going to solve for X. And so what I'm going to do is I am going to bring this over here to the right so I have a place to write. And I'm going to say that X, which remember, X is going to be our concentration of protons, is simply going to be, I'm going to take these two and bring them over to the left-hand side. And so what I'm going to have is the concentration of acetic acid initially divided by my initial concentration of acetate multiplied by my Ka. Okay, now I'd like to know the pH, so what I'm going to do is I'm going to take the minus log of both sides. So I'm going to have the minus log of my concentration of protons is going to be equal to the minus log of this big product, which is going to be the concentration of acetic acid initially divided by the initial concentration of acetate times Ka. Okay, so this is what I want. This is going to be equal to pH, but now we have to simplify this. And the way I'm going to simplify this is I'm going to split my product into two pieces. And so I'm going to say that this is going to be equal to the negative log of my concentration. So I'm going to have the negative log of acetic acid naught divided by the concentration of acetate naught. And then I'm going to have minus the log of Ka. Okay, so that's nice. And then the negative log of Ka, well, that's simply going to be equal to my pKa. Then the next thing I do historically is I take this minus sign and I pull it inside. And when I do that, I'm going to be able to turn this term into the plus log, and now I'm going to have this to the minus 1, which means I now have my acetate ion upstairs and my concentration of acetic acid downstairs. Okay, so that's going to be the derivation. Let's now get some board space so we can collect all of our terms and write this out. And so what I have just shown you here is that the pH of my solution is going to be equal to the pKa of acetic acid plus the log of our initial concentration of acetate ions divided by our initial concentration of acetic acid. So this was all specific to acetic acid, but I could generalize this to any weak acid and turn this into a general rule. And when I turn this into a general rule, I find that pH is going to be equal to the pKa of the weak acid plus the log of my concentration of base divided by my concentration of acid, like that. Okay, and this, of course, is the famous Henderson-Hasselbalch relationship. So this is known as the Henderson-Hasselbalch equation. And what is so cool about this equation is that Henderson and Hasselbalch derived it without understanding equilibrium, which is pretty impressive. Okay, and with that, we are just about out of time, so why don't we wrap it up here and take this up on Monday. You guys have a great rest of your day, great weekend, and I will see you on Monday, and I'm happy to answer any questions.
Thank you.
Thank you, Queen.
Thank you.
Thank you.
Thank you very much.
Thank
Thank you.
Hi, Professor. I just had a quick question. Does KQ have units on it?
Does K have units on it?
KEQ specifically?
KEQ, so
Like an equilibrium constant?
yeah, so equilibrium constants right now, they have units on them, and it depends upon what the form of your reaction is. And so, for example, if you have A, which is aqueous, plus B, which is aqueous, is in equilibrium with C, which is aqueous, plus D, which is aqueous, this is not going to have any units on it, because what we're going to have is that the equilibrium constant, Kc, is going to be equal to the concentration of C times the concentration of D times the concentration of A times the concentration of B. So there, all of the units cancel out. But if I have, for example, HA being in equilibrium with H plus A minus, then I am going to have an equilibrium constant, which in this case is going to be a Ka, and Ka is going to be equal to the concentration of protons times the concentration of A minus divided by the concentration of HA. And so I'm going to have molar times molar divided by molar, and so my units are going to be molar. So it depends how many things you have upstairs and how many things you have downstairs as to what your units are going to be.
Thank you so much.
Sure,
Hi, I had a question.
sure.
Could you go over what you did when you converted the negative log to a plus log again?
Sure. So there, what I had was, so let's just look at that piece. And so what I had was negative the log of the concentration of acetic acid naught divided by acetate naught. Okay, so what I can do now is I can take this minus sign in, and when I bring a number into the log, that turns into an exponent. So this is going to be equal to the log of the concentration of acetic acid divided by the concentration of acetate ions, this whole thing raised to the -1 power. But if I raise it to the -1 power, I'm just flipping it upside down. So this is going to be equal to the log of the concentration of my acetate divided by my concentration of acetic acid. Does that make sense?
Yeah, thank you.
Sure.
Hi, Professor. I just had a quick question regarding, you said we can't use the titration of the strong for the unknown indicator lab. So,
Well, so what I said was, don't try to mix an acid and a base and hit a specific pH. Because what I just showed you is you have to measure out your concentrations of acid and base to unholy accuracy, unless you're trying to make something that's very acidic or very basic.
so are you still doing like a titration in order to find the pK?
So you can do a titration to find the pKa, but what you've got to be careful of is that when you do this under the conditions I gave you, you're going to tend to overshoot by a lot. So you need to think of how you could overshoot less.
Okay. Like, would diluting the bases work?
Sounds like a good idea to me, but your lab.
Thank you.
Sure.
Have a good day.
You know.